Terus kita save ke folder tak?
Oh, dimasukkan dulu.
Iya, jadi nanti kita bisa tarik dari situ.
Assalamualaikum, Pambu.
Waalaikumsalam. Apa kabar?
Ya, baik. Alhamdulillah. Ya, sehat, Pak.
Ya, baik. Alhamdulillah. Begini ya. Ini saja latar belakangnya.
Iya, mantap, Prof. Ada duplikat tak di belakang?
Iya. Ini tidak tahu siapa yang kasih ini foto. Ini tidak boleh kalau ini. Ini saja. Kalau ini. Wah, ini biarlah ini. Karena ini algae ini. Ini waktu industri di apa itu? Di Denmark sama Pak Gun. Oke. Wih, saya ganti baju dulu.
Halo, Peter.
Hi there.
How are you, Peter? You remember me? I'm Yayu.
Now that I see you, I do. It was a little while ago though. So yes. So yeah. Thank you very much for making the connection, and yeah, it was quite a while ago.
Yes, indeed. And how was ETS?
It's great. You know, I think we had tough times during COVID, as everyone did, and we had some financial challenges, but they're mostly behind us. Where we never closed down. We kept the research going. There were a lot of the universities across Australia closed down for at least 6 months, maybe a year. No research, no nothing. But yeah, we had a lot of contract work, so we kept going through COVID safely. And yeah, we're pleased because it was tough. And I assume you guys had similar challenges.
Yes, same as us. And also, I read also that one of the factors that was affecting some of the universities closing down in Australia was of the international students that are not, they cannot go there.
Yes.
So it's decreasing. So yeah, hopefully.
It's getting better now that the borders are open, but it was really damaging for the students that were in country that couldn't visit their families, and also a lot of our staff. So when the borders were about to close, lots of students and staff went home, and then they were never allowed back for another year and a half. And so it was very, very tough for PhD students to be back in their home country trying to finish their PhDs. And they didn't, they had Zoom meetings, but they didn't have access to laboratories. They didn't have access to field sites. It was just, it was very, very unusual.
Yeah.
But yeah, fortunately things are changing where I've just started to get new international students starting. We've had our existing students return, and in another month or so I'll get my first international student starting again. So it's slowly returning to our form of normal, but it's been difficult.
Okay, yeah, that's really nice to hear then. Peter, we actually, I don't know if you are going to mention or not, but for the opening speech later on, we have the new vice rector.
Right.
Yeah, so he is also an Australian alumni.
Ah,
Yeah.
excellent.
Yeah, from geological engineering. So
Right.
is
New.
Professor Adi
And you,
Maulana.
good. That'll be exciting and interesting.
Yeah, I think there will be some Australian connections here, some Australian alumni also attending.
Good. No, that's important, and you know, I think there's been a lot of students in the climate change cluster. I don't have any Indonesian students at the moment, but Martina Doblin does, and I think Justin does. So we've got a number of students, and yeah, we've got ex-students that are back in Indonesia with jobs now. So yeah, it's always good to be able to understand how everyone's moving and tracking.
Yeah, that's true.
But yeah, that was one of our students that she had just started before COVID, and she couldn't get to Australia. She had to stay in Indonesia, and she arrived 6 months ago. So she's still got another year and a half left of the thesis, but she started just on the beginning of COVID, and borders shut, and it was very, very difficult.
Yeah. Okay. I think while waiting for the vice rector, we can start probably. So, yang duluan Pak, saya yang buka atau? Oh, okay. Okay, so we can start now, Peter. Yep.
Okay.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. First of all, I would like to thank Allah Subhanahu wa Ta'ala, the God Almighty, for His grace that we are gathered together in good health today to attend the international webinar series of top scientists here in Unhas. And also salam to the beloved Prophet Muhammad Sallallahu Alaihi Wasallam for his guidance in our daily conducts. The Honorable Vice Rector for Partnership, Innovation, Entrepreneurship, and Business, Professor Dr. Adi Maulana, the Honorable Dean Faculty of Marine Science and Fisheries, Hasanuddin University, Dr. Safruddin, and to the most honorable, our invited speaker, Professor Peter Ralph. For this morning, today we will have a webinar series, but and will be open first, welcome by our Dean, Dr. Safruddin Hasim. Time is yours.
Thank you, moderator. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Your Excellencies, distinguished guests, ladies and gentlemen, good morning to all of us in this special day. As the Dean of Faculty of Marine Science and Fisheries, Hasanuddin University, I am honored and more than delighted to welcome you all to our faculty, and welcome to our collaboration program with Faculty of Science, University of Technology at Sydney, Australia. First of all, let me greet our speaker, the Honorable invited speaker, Professor Peter Ralph from Faculty of Science, University of Technology, Sydney, Australia, and the Honorable Vice Rector for Partnership Innovation, Entrepreneurship and Business, Professor Adi Maulana, and dear participants, it is my great pleasure to welcome you to our Top Scientist webinar series, which is part of world-class university programs at Hasanuddin University. I would like to thank everyone for attending this webinar. It is so unfortunately that due to the pandemic situation, we could not meet face-to-face and entertain you all in our faculty. I would also like to inform that our program today is according with the policy of the Ministry of the Education, Culture, Research and Technology through world-class university program. And Hasanuddin University is now recognized as a world-class university according to the GS World Class ranking. In this opportunity, I would also like to thank Professor Peter Ralph for making yourself available for this webinar. I know that this is your first time giving a talk at Hasanuddin University, but that doesn't mean we don't know you well, because I am sure many of the participants here have now you will through your interesting research and outstanding publications. From you, a very interesting topic, can algae save the planet? I believe there will be interesting answer to this question, and I am sure that talk will be significant and enrich the quality of the webinar and provide new insight, idea, and the scientific information to all participants. It is my pleasure also to remind us that when speaking of algae, if it would remind us how important they are, since they produce 70 to 80% oxygen that we breathe. They can be important food source, and also they are important in mitigating climate change and many more interesting important of algae that Professor Peter will talk about. Ladies and gentlemen, in this special event, allow me also to take this opportunity to introduce you to our Faculty of Marine Science and Fisheries, especially for some of us who have yet visited to the Hasanuddin University campus. It is currently consists of two departments, Department of Marine Science and Department of Fisheries. We have 10 study programs and 18 laboratories. The total students around 2,000 from undergraduate students to doctoral students. The vision is to become the center of development and management of the coastal and marine sources. In total, there are 115 lectures, among which 24 are professors. Well, I am really looking forward to have a nice discussion, and hopefully from this webinar we can start a new collaboration between Hasanuddin University and the University of Technology at Sydney. In the end of this speech, I would like to thank the person in charge of this event, Dr. Yayu, and all her team in the University of Hasanuddin. Our high gratitude also for Professor Peter for the support and collaboration in this webinar. Hopefully, we could maintain and expand our collaboration in the near future. Finally, I wish you all productive and successful day for everybody and enjoy the webinar. and be happy. Thank you for your participation and collaboration.
Okay, thank you very much to the Dean of Faculty of Marine Science and Fisheries, Hasanuddin University, Dr. Safruddin. Next would be opening by our Vice Rector, Bapak, the Honorable Vice Rector for Partnership, Innovation, Entrepreneurship, and Business, Bapak Profesor Dr. Adi Maulana. Times and screen is yours, Prof. Adi.
Okay, thank you, Ibu Yayu. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. A very good morning to everyone. Distinguished moderators, speakers, and participants, especially for our speakers today, Professor Peter Ralph, Dean of Marine Science and Fisheries Faculty, Hasanuddin University, and ladies and gentlemen. It is my pleasure to open this Top Scientist webinar series today. As what Dean of Marine Science and Fishery Faculty has mentioned before, that this webinar is part of world-class university program in Hasanuddin University. So let me take this opportunity as well to wish all of you the very best for 2022. Today's topic is very relevant with our global issue actually, which is climate change. We know that Indonesia now become a host of a G20 meeting in Bali. And then we are also know that Indonesia has set a very ambitious target actually for emission reductions and net zero emissions by 2060 or sooner. And then we are very committed to reducing greenhouse gas emissions by 20% by 2030. And then with our own effort, or around 40% with international support actually, especially from our neighbor Australia. I still remember that about 2 months ago, Prime Minister of Australia visited Hasanuddin University, and then we had a very fruitful discussion, particularly on how to together to combat the climate change issue, which is very crucial actually for Hasanuddin University and also for Indonesia as a whole. And then the topic today, I think it's very interesting, especially for me, because I'm not a biologist or a marine scientist, but I know that because I'm a geologist, so I really also very concerned with the climate change issue. We know that algae as a we can use algae as a carbon sequestration, food, materials, and then fuel. I know that. Yeah, algae also. I think in the future, algae might be our secret weapon to combating the climate change. That's why I really happy when the organizing committee sent me an invitation to open this webinar. And then I noticed that the topic, can algae save the world, which is very interesting. And I do believe that our webinar today will be very fruitful. And then there will be many information, many discussions that we can get in order to increase our concern, on how to combat the greenhouse gas emissions. And then, as we know that the world problems actually can be solved by two things. The first one is the collective actions, and then I think our activity today can be concluded as a collective actions. And then the second one is a human first technology that improves upon a dated way of doing things. We hope that after this webinar, we will have a more intensive discussions on how to combat the climate change. Particularly, we are using algae as our responsibility for our environment. So that's I conclude that one of the human first technology. Hasanul University vision is to become a center of excellence in human development, science, technology, arts, and culture based on the Indonesian maritime continent. So we have a what so-called Indonesian maritime continent. So this topic today is, as I said before, is very relevant with our university vision. That's why I do hope that this meeting will be very productive meetings today. So before concluding, I would like to convey my appreciations to the moderators and then speakers for their valuable time and support in contributing to this seminar, as well as my colleagues in UNHAS, particularly in marine and marine science and fishery faculty, and then for the organizations of this event. We know that we are now in these very challenging circumstances, but we do hope that these circumstances will not limit us to sharing ideas, sharing informations each other. Well, I thank you all participants most warmly for your participations in this occasion. And then with that, on behalf of our rector, I formally open this webinar and wish you all success with this seminar. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much to Bapak Profesor Adi Maulana. Okay, I think we can start now. So I'm also acting as the moderator of this webinar. I would like to start by saying Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. Alhamdulillah, praise and gratitude due to Allah Subhanahu wa Taala, the Almighty God, by whose grace we could gather here today to join in good health the top scientist webinar series here in Hasanuddin University. And salam to the beloved Prophet Muhammad Sallallahu Alaihi Wasallam for his guidance in our daily conducts. I would like to express my thank you to the Dean of Faculty of Marine Science and Fisheries, Dr. Safruddin, and also to Professor Dr. Adi Maulana as the rector representative for opening and also giving a welcome speech in this webinar. Today, Professor Peter Reff from the Faculty of Science, University of Technology, Sydney will be our special guest to give a talk on algae. Hello, Peter. How are you?
Well, thank you. Well, thank you.
Okay, that's good to know. I'm glad that you could make it today. And I think it's winter now in Australia, right?
Absolutely. Absolutely. It's very cold.
Yeah, we also could feel the cold breeze here in Indonesia. Okay, so for everybody's information, I first became acquainted with Peter back in long time ago. I will not say the year, well, 1999. And he was one of my favorite lecturers, actually. Anyway, without further ado, I will read Peter's biography. Background education, Peter earned Bachelor of Science degree from from New South Wales Institute of Technology, NSWIT, in Australia back in 1986, and he got his PhD in marine biology from University of Technology, Sydney, Australia in 1997. Peter is a professor of marine biology at UTS and also an executive director of the climate change cluster in the Faculty of Science. He has led the National Multi-Institutional Commonwealth Scientific and Industrial Research Organization Marine and Coastal Carbon Biogeochemistry Cluster and was a deputy chair of the Sydney Institute of Marine Sciences. He is also the founder of the New South Wales Deep Green Biotech Hub, a member of the Intergovernmental Oceanographic Commission Blue Carbon International Scientific Working Group of UNESCO, and also an advisory panel member for the CHESS Academy of Science Global Change Research Center. Peter also has been engaged in a lot of teaching, research, and also publications. His currently teaching interests are marine primary producers and climate change. Over his career, Peter has made significant advances in the understanding of photosynthetic processes in seagrass, coral, plankton, and algae, growing at their environmental extremes, and he is currently applying this knowledge to develop the algae biotechnology sector and to mitigate the impact of climate change using carbon capture and use technology. Due to his outstanding contribution to research, Peter was awarded the 2012 UTS Vice Chancellor's Award for Research Excellence and the 2018 UTS Vice Chancellor's Award for Research Excellence also. He has authored more than 280 publications, including research articles, books, and book chapters, and has attracted over $15 million in research funding. It's very long. If I read them all here, I will take the time. But from this, we can tell that his expertise, and of course, in this webinar, Peter is going to share with us his experience and expertise. So without further ado, I will give the time to Peter to present his talk. Please, Peter, the time and screen is yours.
Thank you very much, Yayu. And firstly, let me express what an honour it is to be meeting with you all, and thank you both to the rector and the vice rector and the dean for their introductions. So it's always a great chance to meet and discuss opportunities for fixing the planet. And today, what I want to talk about is, as the vice rector said, the secret weapon that we all have access to. So I'll start sharing my screen. And is that the right screen that I'm sharing?
Yes.
It is. Great. Okay. And I'll get a laser pointer going.
How will the algal bioeconomic address climate change?
Yes. Yep. And you can put in quote marks, how will algae save the planet? So it is exactly that topic, and you can see my laser pointer now. Yes. No. I'll work with that. So yeah, thank you for the fantastic introduction, and thank you for the opportunity. So what I want to talk about today is describe why we can use algae, and I'm going to talk about both macroalgae and microalgae, to transform industries and transform society. We have a desperate urgency to fix the planet, and I'm going to talk about a range of different strategies and how we can influence both industries, life choices, and mechanisms by which algae can dramatically alter the trajectory of the planet. And the exciting thing is that the vast majority of the technology is currently available. We need to do a little bit of science, a little bit of engineering to change and to optimize things, but what I'm talking about here is happening now. It's not technology for 10 years, 20 years down the path. And please note, I'm not going to talk a lot about biofuels, because biofuels is one of the greatest challenges of algae, and they're a great opportunity, but that is not a technology that is ready today. But everything else I'm going to be talking about is almost ready today. So to give you an overview of who I am and where all of these opportunities have come from, up the top corner there, you can see this is the Faculty of Science back here at UTS in Sydney. So I head up a research institute that we're now 13 years old. We're about 90 staff and students, and we have 5 teams that cover both climate adaptation and climate mitigation. So teams such as Seagrass Health, Productive Coasts, Future Reefs, and Ocean Microbes are working out how society needs to adapt to climate change, how the resources that support our societies are going to change. The other team the algal biosystems team is developing mitigation strategies. So we do adaptation and mitigation. And I think this is an exciting space for science faculties across the globe. We don't have to just do one or the other. We can do both. And because the transfer of knowledge from people doing fundamental research on adaptation can be transferred to mitigation. So I'm very pleased that we've been able to set that structure in place. So what drives us, what gets us all out of bed in the morning is the global crisis that we're in. You know, once the planet hits 9 billion people, how are we going to feed the planet? How are we going to have sufficient energy? How are we going to have sufficient water? And how are we going to decarbonise the atmosphere? So all of these challenges are immediate now. Some governments around the globe have been a little bit slow, and I'm very proud that the Australian government has stepped up in our commitments to fixing these challenges. The interesting thing is that a lot of times we don't need the government to give us guidance. Industry and society has already taken the lead. And that's the exciting thing for me, is that I'm working with industries to provide them with sustainable raw material to decarbonise the atmosphere. And we don't need government policy to do that. Once carbon taxes come in, I'll talk more about that towards the end, this is going to enhance our capacity as opposed to enable it. The enabling has already happened. Society has moved, certainly in Australia and globally, it has changed. Society demands action, and algae is part of that. I put this slide up just to remind us all of how immediate, and I'm coming up to, oh, this is a terrible story, I'm coming up to 60 years old, and the current atmospheric parts per million is 420 parts per million. That was a couple of months ago. When I was born, the global atmospheric CO2 was 318. It's now 420. So that's a 25% increase in my lifetime. That's the problem that we've got. And this slide shows you the challenges Australia. We're currently in the middle of massive floods. 2 years ago, the entire continent was burning. We have these massive East Coast lows that are cyclones in Sydney. And over my 60 years life, we never used to have cyclones in Sydney. So things are changing and we need to move rapidly. Now, this is an interesting slide to give us an understanding, because I'm going to be talking about a typical Australian life citizen and how they can make changes. This shows us how around the globe we need to understand that different societies, different countries have different impacts. So this is what's called the overshoot days. So at what stage during the year, if the globe functioned at the level of an Australian economy, when would we exploit all of our annual resources? March 22nd, Australia. If everyone on the planet consumed and lived like we do, the planet's resources would be expended less than a quarter of the year through. However, in Indonesia, if we had a lifestyle like the average Indonesian, we would almost go through the entire year without running out of resources. So please keep in mind the things that I'm talking about, because I don't have access to the average Indonesian's carbon footprint. I haven't been able to translate it. So I'm presenting on Australia, but we need to reflect, and I will be considering the vast difference in our carbon footprints for the different countries. So why do I want to promote and drive changing industries to algae? The opportunities here are massive, because what we need to do is not create new industries. What we need to do is to create an economy that takes an existing product and replaces the raw material with a sustainable material. And I'm going to hopefully convince you that algae can produce virtually any raw material for any product that we make on the planet at the moment. And that way we can transform the industries without changing the industries. We just pull out a fossil-derived raw material and slot in a atmospherically carbon-capturing raw material, and that happens to be algae. So it's making a new economy and making a bioeconomy, which is going to be the important thing. I'm probably not going to talk much about genetic engineering, but that is the next step in the bioeconomy, where you do virtually all your chemistry at a cellular level, and you take all of the harsh chemicals out, you take all of the high intensity energy to do the reactions, and you get biology to do it. I'll talk a little bit about some of the ways we're doing it without doing GMOs, but GMOs is also part of the solution. So hopefully for all of the marine scientists in the audience, we all know that there's a massive diversity of algae out there, the seaweeds and the microalgae. And for those not specialists, today, the seaweeds, just treat them as things you see on the rocky shore, as big as your hand, and the microalgae is the green stuff in a pond of water that you can't see the cells. They make it green or red, whichever colour. Now, this is what convinces me that I can find an alga to solve any problem. There's two arrows here. So this is the tree of life. Sorry, the tree of life, bacteria are at the bottom here, below the eukaryotes. So this is everything above bacteria. I've got two arrows. I've got the metazoans and the embryophytes. Metazoans are humans, giraffes, elephants, crocodiles, everything that is a metazoan is in that branch of the tree of life. In the embryophytes, this is pine trees, wheat, rice, roses, all of the higher plants. Every other taxa there is every other eukaryote on the planet. What I've done is I've coloured in the taxa that have algae in them. So reds, greens, browns, blues. There is 300,000 species of microalgae, or sorry, algae out there. If we can't find the cellular biochemistry to make the right product, we're not looking hard enough. So we have a massive resource at our fingertips to exploit. The simple thing with algae is that you take sunlight, some CO2, some fertilizer, and a bit of water, and you can make sugars, proteins, and oils. And they're the basic building blocks of nutrition, but also industrial manufacturing. You can see we can make chemicals, we can make animal feeds, plastics, all range of products. And that's what I'm going to be talking about today. So unfortunately, there's 300,000 species of algae out there, but we're only using about 20 to 30 of them. And that's the problem, that we need to explore and exploit these genetic resources. We need to do that mindfully of where those genetic resources come from. But you can see up the top here, this is the microalgae that have been exploited, and the vast majority is one species, spirulina. We're working with dozens of different ones for different companies, but what we've got to do for human consumption, we've got to prove that it's not toxic, that it is an alga that can be used in food production. Down here with the macroalgae, there's more species that have been exploited because there's been a longer history of human consumption of the seaweeds. But we've got to do more than just consume them. We've got to find chemicals. I was working with my chemist just 20 minutes before I joined this call, and we're looking at how to make foams, and we're looking at which sugars to take from which seaweeds to make a foam. So it's really important that we understand what's out there. Now, the way that we industrially grow microalgae and macroalgae is very straightforward. So we can grow the microalgae in raceways, flat panel reactors, or these massive tubular reactors. One of the companies we're working with in Australia, we're in the throes of building a 100,000 litre tubular bioreactor facility. Probably in the next 6 months, we'll be here and installed in Australia. So these types of commercial production systems, they're all over the globe, and this is one of the ways that we're going to be making algae into the future at an industrial scale. Macroalgae, on the other hand, You can grow it on land, and I think there's a lot of opportunities here for growing it on land because you can strain your loss of fertilizer. You don't eutrophy your coastal area. You can wild harvest. I think this is a limited opportunity, or you can do sea farming. And around Australia, I'll talk more about Asparagopsis in a moment, there is massive tracts of nearshore production of Asparagopsis happening. And this is very, very exciting. So both systems, there's industrially relevant ways to grow sufficient biomass to support each of the industries. This is an interesting way of looking at algae, whether you look at microalgae or macroalgae, they functionally can slot into the same roles, and you can see the products that you can make from the two different sources are almost interchangeable. One of the rules of thumb that I work by is that generally macroalgae, seaweeds, have more sugars and microalgae have more oils. Beyond that, they essentially can make similar products. You can see over the side here, what we're making is we're making proteins at the moment. We're making gels, biofertilizers, biostimulants, soaps, food, animal feeds. We've got some activity in biofuels. We've got a lot of activity in bioplastics and biofibers. The things that are greyed out, I won't be talking about today, but we've got activity across all of these different products that are being generated from algae. Before I get into the nuts and bolts of it, I want to convince you that industry is where the interest is. This is a landscape map that we built. Just trying to think, there's no date on this, but this was probably a year and a half, maybe 2 years old. So what we did is we went out with a collaborator called Olivia Fox and put all of the logos of all the companies that are using algal systems. So whether or not it's in food, whether it's in industrial products, whether it's in nutraceuticals, pharmaceuticals, they are the companies that are already involved. Some of the major players, DSM, IKEA, there is BASF. These are industrial companies that have already seen the opportunities and are already having algal-based products in their production lines. So it's not crazy to be talking about algae as an industrial solution. So what I'm going to run through now is the three biggest ways that society can use algae as a way to mitigate climate change. I'll run through alternate protein, I'll talk about biofuels, and I'll talk about bioplastics. They're the three areas of industrial opportunities. I'm going to finish up talking about carbon capture, because carbon capture is going to have to be a component of mitigation. We are going to have to, apart from replacing raw materials in our industrial consumer society, we're going to have to capture carbon no matter what to get the planet or to maintain the planet within 1.5 degree warming. So they're the areas that I'll run through now. So once again, I apologise, I don't have Indonesian typical consumer data, but reflect back to the diagram I showed you before, where Australia is probably 3 times the carbon footprint of an individual, a typical Indonesian footprint. So this is a survey that allowed me to make a story about where individuals and industry needs to focus its energy. In Australia, our consumption of food is our dominant source of carbon from our footprint. I'll talk a little bit about housing towards the end and transport. I won't talk about motor transport, and obviously electrification. I won't be talking about rail transport. So we'll start talking about food as the beginning point. So one of the problems with consumption in Australia is our preference for eating beef and having dairy. These two sources of food are by far our greatest contribution to our climate crisis in Australia. The interesting thing is it's also the easiest thing for us to address and reduce. There's been some interesting research that literally came out a week ago that compared investment dollars into alternate protein versus investment dollars into direct air capture. Now, these are two ways that we can fix the planet. But for $1 billion putting it into alternate proteins, we can have a massive reduction in the carbon emissions of meat-eating societies relative to the investment of $1 billion into direct air capture. You'll have a modest reduction in carbon. So this is talking about the amount of money that we need to make changes. And I'll talk about direct air capture later on, but dollar for dollar, this is where we should be putting our first money. Now, this is a horrendous image here that shows us the relative amount of carbon emissions for the beef and cattle industry. So China's our greatest global carbon emitter, followed by the United States. And if the beef and milk industry was a country, it would be the third largest emitter of CO2. Now, this is something that many people around the globe have seen, and we are part of that solution. So what the challenge is to take people such as the Australian general public, who are predominantly meat lovers, who have large consumptions of meat, and swap them not necessarily to a vegan or a vegetarian lifestyle, but to this is what we're seeing as a non-beef. So this is an alternate protein lifestyle where we're virtually halving their carbon footprint through their food. And in principle, they don't know what, they're still eating textured meat-like product. And this is a very straightforward way to change their diet. There will, no matter what happens with alternate proteins, there will always be a market for beef. And that's why at UTS, we're working both in the alternate protein and we're working at decarbonising the beef industry. This is an interesting, quite recent development has been the story of Asparagopsis. So Asparagopsis is this red algae here in these containers. A gentleman by the name of Rob Kinsley, back about 20 years ago in Canada, he worked out that cattle that were eating seaweed had less methane emissions. And so what now as a global activity is there is seaweed farmers all over the globe that are now growing this species, Asparagopsis, as a methane reducing seaweed. 1% of their diet, you feed them dried Asparagopsis and the methane emission drops. And methane is 28 times more impactful on global warming than CO2 is. So we need to make sure our remaining cattle herd, which is going to get smaller, has to get smaller. So people will still eat meat, but it'll become more expensive and it will be less impacting on the planet. Forget about the amount of food that we have to grow to feed the cows, to eat the cows. We should be eating the soy, and that's what alternate protein story is. But to keep the cattle industry at a smaller scale, we need to reduce its methane. Interestingly, some of the work that we're doing here at UTS, we're working with the Meat Livestock Australia, and we're working with one of our brewery partners, and we're using microalgae to mitigate methane emissions, and we're doing ruminant digestion trials, and this is quite an interesting piece of work, but we're not doing the seaweed work, which is much more advanced. So I think what we need to do for the food industry is to understand what its carbon footprint and also what its water footprint is. And we can see in this diagram here that if you want to get a kilogram of protein, the best way to do that is through a microalgae. It gives you the greatest amount of protein per area and uses the least amount of water to make that protein. So I think there's huge opportunities for transforming the food industry by eating protein. The challenge is you've got to get your seaweed or your microalgae not to smell like fish, so that you just have protein in the form of a burger or a beef patty or a sausage or textured meat that looks, tastes, smells like meat. And this is some very, very good research that's moving forward. So I'm going to talk about two things here. I'll talk about microalgal burgers and then seaweed burgers. So these are two burgers that are currently commercially available that are microalgae based. So they're using chlorella as the, in the top example, this is Sophie's burger, and the bottom one is using spirulina. These, I think the most interesting one is Sophie's burger, because this is made in Singapore, and Singapore doesn't have a lot of land area. So this is a high intensity, high tech, biotech solution to make protein at scale that can actually feed part of the population of Singapore. Using spirulina in Europe is very, very common for making burgers and other products. The number of burgers that have got seaweeds in them, and I think this is where it's becoming quite interesting, is the seaweed becomes a part of the product, its texture is part of the bonus, whereas microalgae, you just make a protein, and you want to make it smell nothing, no colour, so that's just protein going into these burgers. So there's a wide range of seaweed derived burgers that are on the market, mostly in Europe, where these ones are coming from. This is an interesting company. I've been following this startup for a few years now. They started up as these three young ladies, graduated from University of California. One was a biotech, one was a marketing comms, the other was a accounting specialist. And so they have created prawns or shrimp that are seaweed and microalgae replacements. There's massive problems. I know Indonesia has a large shrimp production facility, and in my former life with my blue carbon hat on, removing mangroves and growing shrimp ponds is a very, very damaging practice for carbon emissions. And what we have to do is we have to stop removing mangroves. We have to rehabilitate those shrimp ponds, and using alternate shrimp is another solution, so that we don't actually have massive loss of mangroves for that. But yeah, the biotechnology solutions are massive in the seafood industry. So there's companies now that are making alternate tuna, making alternate salmon. Because seaweed and microalgae smell like fish, you don't have the problem of odour, and you can actually promote the odour of it. When you're making meat, you've got to get rid of the odour. This is one of the interesting things is salmon now. So you can make an alternate salmon with the flavour, texture. Actually, I'll show you in a couple of slides 3D printing these. These ones currently are extruded, not printed, so their texture is not quite as good. But essentially, you can grow your biomass. You don't have to wait 5 years to grow a fish. You can grow your biomass in 15 days. And this is a sustainable way of using diatoms to make salmon. I mentioned before that getting the algae into raw materials is really critical. So getting it into pastas and just basic protein for human consumption is going to be very, very important. This is where we just don't worry about the odor. We don't worry about its color. It's just a component of everyday biscuits, bread, pasta. This is going to be a key way for us to make food more sustainable. Finishing up with colour, this is our work. So one of the companies in Australia, and actually, I'm not sure that V2 burgers are in Indonesia yet, but they're certainly throughout Southeast Asia. So we're working with this company called V2 Foods to make beef patties, and we're developing some of the colour components to that research. So this is very exciting work where we can help support industry to make sustainable food products that, without society or the consumer realising that they're having a food that has a massively reduced carbon footprint, they still think it's great food. And I think this is the way that we need to move forward. I mentioned before that 3D printing is becoming very, very popular. So there's 3D printing steaks, 3D printing salmon fillets. So you can actually put the layering into it. You can put a little bit of fat into it. So it has the mouthfeel of a salmon instead of a orange tofu, which is what it's like if it's extruded. So it doesn't have the texture. Similarly, with steaks, you can use 3D printers to print different components to give texture and make the steak more of a mouthfeel, as opposed to making mince. Mince is easy. It's just chewy little bits of meat, whereas a steak, you've got to have a much greater structure to it. Okay, so there's some of the algal-based industrial solutions to decarbonising what we eat. I'm going to quickly run through how we're going to decarbonise how we move and travel. This is going to be some areas, there's some big problems ahead, and this is where I think algae's least well placed to solve these problems. So we'll take on flight. How do we have sustainable jet fuels? So there's been an awful lot of work in what's called SAF, Sustainable Aviation Fuels. There's been millions and millions of dollars put into it. There's a lot of interest in how to make aviation fuel sustainable. One of the great problems is we've got to be able to make fuel that doesn't compete with food. So we cannot take a food product and turn it into fuel. And we also shouldn't be growing the substrates, the oil crops, on land that are competing with human-based food production. So that's our challenge. How do we get around this? What I show you up the top here is why we need to actually focus on advanced fuels and why aviation needs some very, very specialised fuels that have got extremely high levels of energy, but they also don't weigh much. We don't need to worry about road transport. We don't need to worry about gasoline for cars, for trucks. That will all be electrified. We do need to worry about navigation and shipping and aviation. They're the two parts that need high intensity, high energy fuels that don't weigh a lot. And this is where sustainable aviation fuel goes. Interestingly, the shipping systems could be supplemented with batteries, but the cost and the weight is just too great. I was recently talking with a multinational company about putting some carbon capture units on ships. So the ships continue to use fuels. It'll be a sustainable source of bunker fuel, but the carbon isn't just vented into the atmosphere, it could be captured on the ship. I'll talk more about carbon capture later. I think one of the places the government comes into play is here with the US investment in the Great Green Fleet. So the US has regulated that its sustainable naval fleet, which is a part of its fleet, will only dock and visit countries that can provide it with sustainable fuel. So you cannot refuel this part of the fleet with bunker fuel that's derived from fossil sources. It has to be from sustainable sources. And unfortunately, this usually ends up being corn and rapeseed and a lot of agricultural crops. So the challenge here is there's a whole bunch of potential products that could be turned into fuels. And down the back end here, all of these ones are forestry based. So we need to have large amounts of forestry that can then turn into fuels. We have, unfortunately, things here, we've got cooking oils and tallow and functionally plant oils. These all should be used for human consumption. We shouldn't be transisterifying those into fuels. We can take algae, but algae needs to be grown on non-arable soil so that it's not competing with food production. That is one potential source. But we've got so many different players, and there's such urgency by the aviation industry to get sustainable aviation fuel. Algae's not in the picture. Every one of those other solutions is being capitalised, invested and developed. So in the near term, we're going to have to rationalise what sustainable aviation fuel is. Just because it's not fossil derived doesn't mean that it's good for the planet. And this is critical, the issue of the source of the sustainable fuel. One of the challenges with biofuels is not the technology, it's just that fossil-derived fuels, you basically put a drilling rig down, you access the raw fuel, you bring it to the surface, you put it through a catalytic cracker, and you differentiate which parts of the fuel you want. This diagram here, if you imagine that is where you start for fossil fuels. So you drill for it and you put it straight into your separation technology. To make algal-derived biofuels, you got to do all of this stuff in the box here. So you've got to set up a pond, you've got to separate the biomass, you've got to remove the fractions, you've got to centrifuge, you've got to extract the lipids, and then you're at the same point that fossil-derived fuels come from. So we've got all this upstream processing that costs a lot, and that's why we're not cost competitive with fossil fuels. If we took the subsidies off the fossil fuel industry, they've had 100 years to write off all of their infrastructure. We've got to build it now to make it. So it is possible to do it, but it's because it's a commodity and the prices are subsidized. I don't think for a very, very long time we're going to be cost competitive with making biofuels. So everything else I'll talk about is other industries, not biofuels. One point that I'll make is this point here, the centrifuge is 40% of your costs. The electricity to separate 0.01% of biomass from a litre of water is massive. So that's where the cost is in the centrifuging. One of the exciting things that for Australia, we've got opportunities is if we follow an Israeli example and we have our biofuels production supported by a massive photovoltaic array. If we can get cheaper non-carbon emitting energy, we can make biofuels. There's no problem. But it's...
Morning, Dr. Ayu.
So that's one of the challenges that we need to move forward with. So the last part of the story is the household. Now, it's not us living in the household, but it's the building. What can we stick into buildings? And this construction industry is about 40% of the global carbon emissions. The construction industry could be a massive sink for carbon. Now, I'm not going to talk about all of these things here. I do separate talks on the construction industry. What I'm going to talk about today is opportunities in the clothing industry. It's a smaller talk, but if anyone wants to talk to me later about how to put carbon into buildings, this is my current major thrust of activity. So where can we make our clothing more sustainable? How can we use algae to replace cotton? For example, cotton is an extremely water-intensive fabric to make. We eutrofy all of our rivers in Australia because we put so much fertilizer on it. We can make T-shirts, we can make all these fabrics using macro and microalgae. So there's startup companies all over the globe that are starting to make these products. Bloom is a company over in the US that is making a whole range of shoes now. Now what they're doing is they're making foams and they're putting algae in as the filler. There's still fossil-derived components in these plastics, these foams that they're making, but they're getting rid of waste algae and using it as a filler in these products. The interesting system up the top here is they park this vacuum cleaner beside a eutrophied lake. They separate the algae from the lake water, put the lake water back, and then make products with this. So it's a very, very simple technology, but it's very, very effective. What we're doing at UTS is we're making a lot of bioplastics out of macroalgae and microalgae. We take the sugars, we take the oils from these, we do some clean chemistry, green chemistry, we extrude the pellets, and then we injection mold them. We also make fibers, so we create what we call a dope, and then we extrude the fiber, and then we're in the throes of weaving. So my dream is to make clothes, and this is a crazy dream. I dream of making clothes out of sewage and atmospheric CO2. I don't want to use fertilizer that I want to use on crops to feed people. I want to have a sewage treatment plant where there's nitrogen and phosphorus. I want to strip atmospheric CO2 from the air, and I want to make cellulose. I want to make fibers to make clothes. I think this is going to be one of the big sustainable solutions. Circular economy, we're not wasting waste. This doesn't really show the excitement of our plastics, but we make lots of plastics now. These are seaweed-based plastics. We're having them extruded in China at the moment. We've got partners. We make plastic bags. We make injection molded plastics. We make biodegradable plastics. We make permanent plastics. We have plastics that have limited fossil components in it. We have plastics that have no fossil components in it. So it's a very, very active space, and this is where you can stick a lot of products into buildings, the carpet tiles, the laminated tables, the wall panels, everything we can have carbon stuck in it and stored. One of the other plastics that's important is cyanobacterial plastics, and we've been making a whole range of these from cyanobacteria, not microalgae. But the interesting thing that I want to highlight here is the importance of screening. So screening is where you have a strain of cyanobacteria and you mutate it and you see which one makes the most of that compound that you want. This is a very, very exciting space for biotechnology, is high throughput screening and automation. So to show you what we've done in the past, we have selected different species of corn to take the traditional corn into the massive corn that we have these days, to take the boring mustard plant and turn it into 10 different types of vegetables. We can do that now with microalgae. So we can combine different species. We can mutate them and find ones that make more oils, that make more pigments. So this is going to really revolutionize how we move into the industry. This is some of the recent technology that we've just put into our facility here. So we've got a fully automatic phenomics facility. The robot controls the entire system. All of the algae lives in 96 well plates, or for seaweeds, they live in 12 well plates. And the screening, the chemical characterization is all run by robots. And this is going to fast track us to some very, very exciting solutions for industry and global solutions. Okay, in my last few minutes, I want to wrap up with how all of these suggested ways of changing society and industry can actually decarbonize the atmosphere. I'm going to talk about carbon trading. I'm going to talk about taxes and how the planet is going to change the way that we value carbon. So the short answer is we need to do more than just change industries. We need to have the technology to remove atmospheric CO2. This is the problem that's highlighted at the end here. We cannot just do removing, we can't just change our production systems to solar. We can't decarbonize our energy production system. There's already too much CO2 in the atmosphere, and trees and plantings aren't going to be enough to remove that atmospheric CO2. So we've got to have technology that puts a dollar value on the carbon. It doesn't have to be a tax, but we've got to remove massive amounts of carbon from the atmosphere whilst not putting new stuff in the atmosphere. So this is a concept that I've been tossing around, is everyone wants to decarbonise, and I'm on lots of working groups to decarbonise the state, to decarbonise Australia. But what I think it really is defossilise. We need to be thinking about not using fossil sources of carbon and seeing carbon as a useful building block of society. For food, everything I've spoken about uses carbon. So we should be defossilising, not decarbonising. We should be seeing carbon as a valuable resource and mining it and using it, recycling it, and also storing it for long periods of time. But I think it's this challenge of seeing carbon as the villain. Now, we've got a bunch of ways that we've got to get it out of the atmosphere. We can capture it into trees, store it for 70 years. We can capture it into biochar, bury it in the ground and it doesn't come back. We can have direct air capture systems that chemically remove CO2 from the atmosphere, then in a solid form, bury it underground. There's a whole range of technologies. What I want to see used, or more used, is carbon capture and use. So catch the carbon, put it into something, and have that thing in society cycling around and attracting a carbon credit, because while it's not biodegraded, it's storing the carbon, and we can stick that carbon into a whole bunch of products. So this is a summation of the cost of carbon capture and how big the opportunity is. So anything below the line means that you can actually get paid to capture that carbon and stick it into a product. So there's biochar, there's timber and forestry. At the moment, if you capture carbon and you stick it into algae, you're going to be paying at least $200 a tonne. Now, if the carbon price is in Australia running at about $30 a tonne, in the European Union it's running at about $90 a tonne. You can't make, pardon me, money capturing carbon and sticking it in algae without making something else from it. So this is where I want to use the carbon and make stuff. So we started out 3 years ago working with a brewery, a local brewery in Sydney called Young Henry's, where they wanted to capture their carbon and make stuff with it. So we developed technology for them, we capture their carbon, and we're now making stuff for them. That has gone all over the globe. I have had hundreds of emails from breweries all over the globe wanting to do this. I thought, this is good. This is the technology that we need to move forward. We need to catch the carbon and make stuff. So we've developed our thinking a little bit further. And so what we've now built, and in the next month, if any of you come to Sydney, you'll see that shipping container sitting on a street out the front of UTS. That shipping container is a carbon capture and use technology. It's algal based and we can use it for direct air capture. We capture atmospheric carbon and we make green stuff out of it. We can plug it into a generator, capture the flue gas, make green stuff. We can have an anaerobic digester, capture the CO2, let the methane go off and run engines and make green stuff. This is the beginning of using carbon capture and use. So about 10, in the introduction, it was explained that I used to spend a lot of time working for UNFCCC, working for different groups on blue carbon. So I helped to develop the blue carbon methodologies and the technology. What I'm now starting doing is I'm working with a new group called Estonium. This is manufacturers based out of Europe. And what we're developing is verifiable carbon footprints for products. So this diagram here shows what's going to happen in Europe. We've got a carbon intensive product coming from Australia. We've got a low carbon product coming from Europe. They both move into Europe, and if there's no carbon adjustment mechanism, you're going to buy the Australian carbon intensive steel because it's cheaper. What the carbon border adjustment mechanism is going to do is when the Australian steel comes in that's carbon intensive, it's going to have a high carbon border adjustment tax on it. The low carbon from Europe is going to have a low cost, and so therefore my Australian product needs to be decarbonised. And this is the way that Europe is going to transform the investment in industries so that industries that export to Europe that are not sustainable, that are not low carbon, are not going to survive. So this association called Estonium is building the regulatory processes. Every second week I have an hour-long discussion with people from around the globe, and we're building the processes for it. What we're going to be able to do is allow a manufacturer to say, I want to source my raw materials from this supplier because they are low carbon, and therefore my product is going to become lower carbon. We're going to encourage the industries to seek out and find the best suppliers that will reduce their costs and maximise their markets. So this is a way that we're really going to streamline changing the planet's industrial production for lower carbon. Here's an example that I showed to the Estonium group. What we can do is we can make CO2 when we make products, put CO2 into the atmosphere, and then we can offset it with trees. The planet will run out of trees, space to plant trees to capture all the carbon that we've got. So offsetting with terrestrial sinks is not going to fix the planet. Alternatively, what we can do is we have production, capture the carbon, it goes into the trees. We then put the trees into a biorefinery and we make reduced carbon products that goes into construction. We can do the same thing. CO2 goes into that box that I showed you before, which we call the green genie, fixes it into algae, we make a product. We can do the same thing with seaweeds. We can make a product and it goes into the industry, into the manufacturing, into the construction industry. So this is a really exciting concept where, based on blockchain, a emitter emits CO2. It's captured by a tree, by algae. It's verified. That blockchain then takes that algae to a manufacturer. They make these things. That verifier proves that that carbon is in that product. And so now people can get offsets. You're not going to have an offset for 100 years, but if you've got a 10-year offset for carpet in your office that stored atmospheric carbon, this is the way that we can incentivize industry to change. And I think this is going to be what's going to happen over the next 5 years. So I hope I've shown you a bunch of opportunities for changing the planet. I hope you've seen seaweed and microalgae all over the place. I know that Indonesian researchers have got capacity and knowledge in seaweeds and microalgae. And I think the opportunity is understanding where those industries are, domestic and overseas, and who you need to work with to position their industry transformation. So industries are desperately looking for all of these changes that I've just described. And every country, every university needs to be finding industry partners that desperately want these opportunities, because I've seen such a dramatic change in our needs and opportunities in the last 2 years, literally. I've been gearing up for it for years, and 2019 was the changing point for us, so 3 years ago. Before that, I could have knocked on the doors of any number of companies saying, I've got algae this, I've got algae that. And they went, yeah, that's cool, that's interesting. But now for the Green Journey, we've got 10 industry partners desperately wanting to invest in it and to have that, whether they're working for a mining company, whether they're working for a construction company, a sewage treatment plant. The technology is here. It needs some fine tuning and industry wants it. So I hope that gives you guys some motivation and some ideas on what could be done with industry partners. And I'm going to finish by acknowledging the parts of the team that do all the work, because as Yayu knew me 20 years ago, I was at the bench and I was doing science, but these days I facilitate science, and this is the team that did most of the work that I've shown you, and some fantastic chemists, some fantastic biologists, and this is what we need to train in the future, is the next generation to get industrial transformation using algae. So I'll leave it there, and I'd love to entertain any questions that anyone in the audience has. So thank you for your time. Thank you for listening. Thank you for the opportunity.
Okay, thank you very much, Peter, for a very, very nice and interesting talk. And I'm sure there are already some people are curious and would like to ask some questions more about the topic. Anyone would like to ask questions can raise their hands or through the chat room. Can I see, are there anyone raising hands or reading? Oh, I'll read the chat room. I'll check if there is.
Wow, there's lots of stuff in the chat.
Oh yeah, there's one from Ibu Kurniati Umrah Nur. Raise hand. Okay, please, Ibu Kurni.
Thank you, Ibu Yayu. Hi, Peter. Good morning.
Hi.
Hi. Thank you for this opportunity. The one that I want to ask is about single-cell protein as a protein source for aquafeed. Yep. What do you think about that? Do you think it's feasible in the future to use the biomass from microalgae as a protein source, as a low effective, as cost-friendly protein source for the aquafeed? And does the climate change cluster have developed this thing? Thank you, Peter.
Fantastic question. Thank you. Yes, we're working with a Vietnamese company in aquafeed optimization, and I think there's huge opportunities for the replacement of fish meal. So fish meal is a terrible base material for growing anything in the aquaculture space. So what we have to do is replace fish meal. Now, the problem is fish meal runs at $600 a ton, and to get algae meal at, pardon me, $600 a ton is a little bit tough. So we've got to find cost. We can't replace all of the protein with microalgae. We have to have other sources, but what we've got to do is we've got to use the microalgae as the trace elements and the amino acids. But the other exciting thing with the aquaculture is the seaweeds. And there's, once again, I don't think at this stage we can replace the entire biomass. We can't grow it at less than $600 a ton. But what we can do is we can put it in as a feed supplement. And one of the aspects of animal husbandry, whether it's fish or cows, is how to reduce the use of antimicrobial or to prevent antimicrobial resistance. So the prevalence of pharmaceutical grade treatments to aquaculture and animals is massive. The opportunities with seaweeds with a thing called sulfated polysaccharides. So the sugars that have got sulfur on them, they're fantastic antivirals, antimicrobials. And what we should be doing is putting little bits of seaweed in the feeds of the aquaculture, and that'll reduce our use of antimicrobials. That's also going to help. Nothing to do with saving the planet with carbon, but making the industry more sustainable and helping the quality of the product for us humans, because we don't want our shrimp, our fish to be loaded with antibiotics when we eat them. So yes, lots of work there. Great area.
Yeah, so still a long journey to be there.
No, the journey's started and the solutions are happening. They're not commercial yet. But that's a great opportunity for the universities, because if we're a little bit advanced, industry goes, well, okay, I'll fund this much if you're already halfway there. If we know nothing about it, then industry gets scared and they go, we're not prepared to invest all of that money to solve the problem. But if we can convince them that we're here, I find industry says yes. So it's the challenge of getting enough, I call it proof of concept, minimal variable product. So prove to an industry that you can half do it, then they'll help you do the rest.
Okay. Thank you, Victor.
Thank you.
Okay. Thank you very much, Bu Kurni. And we have some more questions from the chat room. There is, okay, I read one question before. Here's one from Prof. Budi. I would like to get more detailed explanation about the types of algae that can be used for degradable bioplastics, and what are the possibilities of the serious production scale and the cost of substitution with ordinary plastics.
Okay. Yep. Sorry, I'm not running away. I'm getting my show and tell. So that is pellets that go straight into a production facility. So we have an extruder, we make those pellets, and as I said, we send them to China, to other groups, and they make our plastics. So the answer on its utility is absolute, put into an existing machine. As far as scale, we are working with one type of plastic that one industry is making a ton a day of waste algae that we can turn into plastic. So a ton a day is a good starting point. So you have a few of those kind of scales of seaweed and this is seaweed, making that amount of biomass for a reason, we can turn that into plastics. So the plastic industry is massive, and what we need to do is we need to start by creating boutique plastics. So biodegradable plastics, high value plastics for packaging, things that people will pay a small premium for. And this is happening now. So I don't have to find a partner to grow my algae to make the plastics. I start the other way around. I find another partner who's making lots and lots of algae, and I say, give me your waste and I'll make something with it. That's what we're becoming quite well known for, is we take our partner's waste and what's called valorize it. We find next products that we can take out of it. So we're giving them an extra income stream. And it's better that they've grown their algae, they've taken what they want out of it. And if we didn't do something with it, they'd stick it on the side of the river and it would break down and put all that carbon back in the atmosphere. If we take their waste and turn it into plastic, that carbon's not going back in the atmosphere. So I can't tell you which species of algae it is, but it is seaweeds that we're working with for making these things. Oh, sorry, that's a fibre.
Okay, thank you, Peter.
Thank you, Peter.
Prof. Budi.
Thank you.
Yeah, okay. So it's like what Peter said, not wasting waste, yeah?
Not wasting waste.
Yeah, they're all usable.
Yeah,
Okay.
absolutely.
Are there any more questions? Oh yeah, there's one from Yusnaini from University of Halo in Southeast Sulawesi from Kendari. She said, thank you, Mr. Peter Ralph. Course material is essential to address global warming. How to determine the function of algae in reducing carbon? We know that algae have a very short life. Thank you. From Halo University.
Yeah, and I think the short life of algae is part of the solution, because you've got to make sure you do something with the biomass. You can't just let the algae grow, the carbon stay in the algae, and then for it to die, because that carbon's back in the atmosphere 2 days later. As soon as the bacteria break down the dead cells, that carbon's no longer removed. So yeah, they're absolutely right. It's all about short life cycle, and the short life cycle plays into our hands. You know, that means that we can double the biomass every day, and that's why photobioreactors are very effective. We can make huge amounts of biomass very, very quickly, but if we let it degrade, then we've wasted our time. The carbon's back in the atmosphere.
Okay, thank you, Peter. Ibu Yusnaini, did you hear the explanation?
Pak Yusneni.
Thank you very much, Mr. Peter.
Sorry.
Kasih, Bu.
Yeah, okay, thank you, Pak Yusnaini. I thought Peter, I thought it was a female, but actually it's a male. So, okay, are there any more questions from the audience?
If I may, Bu Yayu.
Let me see. Pak Jamaluddin.
Jamal, Bu. Yeah.
Pak Jamal. Yeah. Thank you, Pak Jamal.
Yeah.
Please, Pak Jamal.
Yeah, thank you, Bu Yayu, as moderator for this opportunity. Good morning, Prof. Peter. Very interesting talk. My name is Jamal from Faculty of Marine Science and Fisheries, Universitas Hasanuddin. So, by any chance, Prof. Peter, have you ever visited Indonesia or Makassar?
I've visited parts of Indonesia, but not your area, no.
Yeah, I thought you ever visited Makassar, because you know, in Makassar we love meat a lot. So you mentioned that earlier that the nation of cattle industry is actually producing a lot of greenhouse emission that could be really harmful to the mother nature. So you also mentioned in your presentation that there is opportunity for the decarbonizing the cattle industry by using typical seaweed. You mentioned that Asparagopsis taxiformis and also Asparagopsis armata, if I'm not mistaken.
Yes.
So I wanted to know if how is the development of this seaweed research in Australia? If they are already implemented in the cattle industry or not?
Yes.
And also, I also would like to know if it's possible to grow that kind of seaweed species in tropical countries such Indonesia. If possible, of course, we love to develop the cultivation of that seaweed, because there is also, I think we have to be responsible if we eat the meat, and then I think we should also try to reduce the greenhouse emission that produced by the cattle industry. Last one. So also interested about one of the point of your side about the offset. So one way to offset the carbon is, you mentioned that by fertilizing the ocean. So I would like to know more about how to fertilizing the ocean in relation with to reduce the carbon. So that's for now. Thank you, Professor, and thank you for the moderator.
Okay, so Asparagopsis, how to reduce the cattle industry, and ocean fertilization. So I'll start in that sequence. So Asparagopsis in Australia is extremely advanced. It's very, very rapidly growing. There's a large number of growers in Australia. I think we might have had our first meat steak that was the cow was grown on Asparagopsis, and there was a steak. So we don't have lots of product, but we've certainly got massive interest from farmers to get it, and lots of growers around Australia wanting leases, wanting technology to be able to grow it, because it's a tough algae to grow. It's got a very complex life cycle, so it's not simple to grow. Can you grow Asparagopsis up in Indonesia? I think the species, I know that in Australia we've got temperature-based gradients where Taxipholis and Amata grow, and I don't know whether or not it will grow even further into the warmer waters. So I don't want to, but I know that Asparagopsis grows around the globe, but whether or not tropics, it may be a little tougher. Ocean fertilization. Okay, ocean fertilization is an extremely bad idea. We should not be fertilizing the ocean. So the concept is you put nitrogen into the ocean, it encourages a greater bloom of algae. The algae settle, they sink to the bottom, and they take the carbon to the seafloor. Fundamental problem there is, yes, you put nitrogen into the water column and you'll get an algal bloom, but you don't get carbon going to the seafloor. Bacteria break down the cells, the carbon's back in the atmosphere. You create all kinds of weird, unhelpful algal growths. So I know it was on my slide as one of the strategies for fixing the planet, but it's a very untested strategy that I don't think we should be investing in using ocean nourishment or fertilization. There's many better ways of stripping carbon than putting nitrogen into the ocean and hoping that something happens. I hope that answers your questions.
Yeah, thank you for the answer. So, Prof. Peter, you mentioned that the Asparagopsis research in Australia is actually quite advanced. So, if possible, I would like to send you email after this. I would like to know if you may have colleagues that you can introduce me, or you, even if you know some technology for cultivating this Asparagopsis, it will be wonderful for us, and we can possibly try to have that. Although you mentioned that it might be difficult, but I think it's quite interesting to know whether we can grow it in Indonesia. So
Yes.
thank you for your time.
Well, please send the email. I've got colleagues in my institute that are seaweed experts that will know exactly what's happening. So I'll be able to get an answer.
Okay, thank you.
No
Thank
worries.
you, Bu Yayu.
Okay, thank you, Pak Jamal. That sounds like a nice start there with UTS and UNHAS, hopefully, for a collaboration later on. Okay, next, do we still have some more raised hands or questions in the chat room?
There was one question on biodegradable plastics.
Biodegradable?
Yeah, I want more details about the types. Oh, well, that was the types of algae, and I couldn't go into that.
Yes, yes. I have delivered it to you.
Yeah.
Any more raised hands from the participants online? Okay, so we don't have more questions or types of things. Okay, so we have no more questions, and well, I thank you very much to Peter for your time and for a very nice and interesting talk. And I'm sure that we have learned a lot from your talk, and that hopefully that we could.
Excuse me.
Sorry, anyone? Is there any?
Yeah, can I share something and maybe ask some question to Dr. Peter?
Okay, who is this, please? Sorry, I cannot see.
Okay, my name is Waiba. I'm from Haluola University.
Oh, okay,
in Kendari.
Bu Waiba. Okay, Bu Waiba from University of Haluola, Southeast Sulawesi in Kendari. Yes, please, Ibu Waude.
Okay, first of all, thank you, Dr. Peter, for the presentation. It was very excellent presentation. I want to share something about the microalgae culture. I've been researching and experimenting with microalgae culture for the last 5 or 6 years since I finished my PhD. And the main problem for the microalgae culture is, apart from the nutrient need for the specific the species, also the harvesting techniques for the microalgae. It was very tough and very difficult to harvest like the large biomass. I never been like my students already cultivate up to 9 liters of microalgae of spirulina. But then for other species, we've been experimenting like 1 liter culture, and it was very difficult to find the right method to harvest the microalgae. Maybe this is the main bottleneck, I think, for producing microalgae biomass for several applications. And I think if you have some insight about this or experience, maybe you can share with me and all the audience. It will be very, I will be very grateful. Or maybe you can show us some technology that you use to harvest microalgae to get the most benefit of the microalgae. Thank you so much.
That's a great question, and it's as you say, it is the biggest question for microalgae. So microalgae is not economic. For most products, because of the cost of harvesting. Harvesting is really, really expensive and really difficult. So first thing is one of your species is the best algae to harvest. You're working with spirulina because spirulina forms long chains. It's not a single cell and you can harvest it. So some of my colleagues here at UTS, we've developed a technology for harvesting spirulina, and it's very cheap. Obviously, it works at hundreds and hundreds of litres, thousands of litres. So we're working on how to harvest a pond, not a litre. But yeah, spirulina is possible with simple physical harvesting, nets and meshes. Whereas microalgae, single cells, you can't harvest with a net. So what we do is we do flocculation. So we do organic flocculation, so chitins, chitosan. We put in some polymers. We're developing synthetic polymers that change the electrostatic attraction of the cells and precipitates or flocculates them and settles them. So yeah, there is technologies. If you send me an email afterwards, I'm happy to send you some of the papers on flocculation. So I think flocculation is, provided you're not eating it, it's not going to animal feed or human food, flocculants are the best strategy because they settle the cells out really quickly and they reduce your harvesting costs dramatically. But I don't want to eat flocculants at the moment. We haven't developed well, chitosans is fine. That's edible, but other synthetic flocculants are not edible.
Okay, thank you. I'll send you an email.
No worries.
Thanks.
Okay, thank you, Bu Iba. There's no more questions, but I had one in mind, especially, well, they are very interesting talk, Peter, but what I catch one with I think is interesting also because you mentioned about the CCU, carbon capture unit that you have.
Yep. And
you mentioned that it's like a box outside of the UTS campus. Is that in the city campus?
Yeah. Yeah.
How effective and efficient are they, and how many boxes do you have?
So we're building our first. It's a shipping container, so it's a standard shipping container, and it will do at the moment about 7 tons of carbon per year. So we'll change the chemistry of it and we'll increase it. We hope to be able to get a 10 times improvement over the next couple of years. So it's modular, and depending on the amount of carbon that an industry makes, they put 5 or 10 units to capture their carbon. But yeah, at the moment, where the prototype that we've got is doing 7 tons a year.
Okay, so it's like having planted trees there, isn't it?
Yeah, it's like having planted trees just in a shipping container. So small footprint, you can stack them on top of each other and they make green stuff. So the product is they suck in gases or air and green biomass comes out the other end. You got to do something with the green biomass, but that's what we spoke about in the whole of the lecture. It was all the things you can do with the green biomass. So this technology, I think, is going to be very, very useful for direct air capture, but also industrial gases. So exhaust gases, methane from anaerobic digesters, anywhere where you've got a brewery, where you've got concentrated CO2, you can capture that CO2 quickly and easily.
What's the size of the box?
It's 20 feet. 20-foot shipping container is the box.
Okay.
So
that's quite large, yeah. 20.
Yeah, but to get 7 tons of carbon, you're going to have a much bigger forest.
Yeah.
To capture that same carbon.
Yes, yes, true indeed. Yeah. Okay. Thank you very much, Peter, for a very interesting talk, and I hope that everybody also have gained more new informations, and also have their minds for what they're going to do for their research later on. And so, okay, I have to give this back to the
Excuse me, Buya.
University team. Yeah.
Is there any time for me to have a short?
Peter, do you think you still have?
I'm fine.
Oh, okay. Okay, please, Bu Nadiarti.
Okay, thank you, Peter. I'm sorry I can open my camera. It is very interesting topic, and I know you have high technology on this. My question is very simple. Is there any possibility for us to come visit your university for benchmarking or a short course to learn more deeply about your technology that you have applied now? Thank you.
Yes, there's always possibilities. Short courses, it's a really, I hadn't considered it. It's possible that the kind of content, because it's a whole institute, there's chemists, there's me, there's biologists, there's a whole range of things. So I suppose there is a possibility for doing a short course if there was a group of people that wanted to come across and learn. We'd be absolutely open to that, because I think part of it's not a challenge, but part of my motivation is to ensure that the technology that we develop can be transported and exported. So, for example, one of our programs in our bioplastics, we're working with Philippines fishing communities and villages. I want not all of our technology to just be developed in Australia. We're developing the technology to make the plastics in the Philippines. So we will be training the seaweed farmers of the Philippines how to grow their biomass, how to process their biomass. So I expect this kind of stuff will be coming out of a village in the Philippines. So we're going to be teaching those people how to do that. So I think there's a lot of opportunities there. And the technology needs to be flexible and not inaccessible, because we're not going to fix as much of the planet as quickly as we can if everything requires massively expensive photobioreactors and multi-million-dollar things to solve these problems. We've got to have them as being versatile enough to be implemented in many, many different countries and situations. So, a long answer to a short question, but yes, I think there is possibilities there, but I haven't considered it before.
Yes, thank you. Thank you, Peter.
Okay, thank you, Bu Nadiarti, for bringing this up. So I think it will be, we can talk about this later on, further on, and hopefully that we can get a nice collaborations out from this webinar.
Yeah, I think the challenge, the opportunity will be students. Finding finding students to work between the two institutions, the two areas. That's the fastest way I've found for implementing technologies in other countries, because the student, provided the student is not trained in technology that's inappropriate or it's not going to happen in the other country, that enables us to have the conduit to make it happen. And that's what I was describing, and I think before we spoke on the seminar, Yo-Yo and I were talking about one of the students that's in UTS. She's an Indonesian student and she's taking technology for fisheries management that she's learning here at UTS back to Indonesia, because I think she's had a permanent position in a government instrumentality for fisheries management. So that level of training is really important, and that's a quick way of technology transfer, but appropriate technology transfer.
Yes, indeed. Okay. Before I ask again for closing, is there any more questions from the audience? Okay, so everybody is satisfied now, and maybe can go home with, oh, okay, I want to do this, I want to do that, based on Peter's talk, I'm sure. Okay, so please give a big applause to Peter. And thank you, Peter, for your time, sharing your knowledge with us. And I'm sure that will motivate us in strengthening our scientific capacity. And I apologize for any inconveniences during the webinar. Before I close, there is a message from the world-class university team of Unhas, Ibu Israini.
Yes.
Okay.
Ibu. All right. Thank you very much, Prof. Peter and Dr. Yayu, for your valuable knowledge and time. And as our appreciation here, can you see my screen?
Oh, yes. Yes, 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 yes.
All right. Yes, as our appreciation, the Vice Rector Hasanuddin made this to Prof. Peter for sharing his valuable knowledge to our students and lecturers in Universitas Hasanuddin. And don't be worried, we will send this certificate by email as well.
Fantastic. That's greatly appreciated. Nice gesture. Thank you.
Thank you very much. You're welcome, Professor.
Peter.
And all right, ladies and gentlemen, before we officially close our webinar, we want all the participants to open your camera because we want to take photo with our distinguished speaker, Prof. Peter.
Okay.
And I will count in 10 seconds, please, everyone. Okay, I think. All right. Okay, we now have 7 slides. I will count. Everyone? All right. Yes. All right. 1, 2, 3. Cheese. And the second slide. 1, 2, 3. And the third slide. 1, 2, 3. The fourth. 1, 2, 3. 1, 2, 3. 1, 2, 3. And the last slide. 1, 2, 3. I think all right. All right. I think everything is awesome today. We finally come to the end of today's agenda. Let's close the webinar by saying alhamdulillah, alhamdulillah rabbil alamin. And those are the agendas we have presented to you all this morning. We hope you learned something, and thank you very much for your attention. Thank you very much, Professor Peter. See you on the next occasions. And Ibu Yayu,
Yeah.
do you have any statement before we close it? And Prof. Peter?
No, thank you. Thank you, everyone. I had a great time, fantastic questions, and I look forward to answering all the emails and finding opportunities with you all. So thank you for your time.
Okay, thank you, Peter. Goodbye, everybody. Stay healthy, everyone. Thank you, and hope we'll be seeing again in the next webinar. Bye-bye. Assalamualaikum warahmatullahi wabarakatuh. Bye, Peter.
Waalaikumsalam warahmatullahi wabarakatuh.
Yeah,
Thank you, Peter.
Can. Oh, sudah ditutup. Oke, izin leave.
Ya, izin leave, Ibu. Izin live, Bapak Ibu.
Terima kasih
Insya Allah nanti.
Bapak Ibu atas kehadirannya.
Insya Allah nanti sertifikatnya kami kirim lewat email beserta PPT-nya, Ibu.
Oh iya.
Iya.
Ini Ibu Sri nih yang sering kontak saya ya?
Iya,